Assalamualaikum warahmatullahi wabarakatuh. So I'm Irfan Nazmi and our group will present about the GPU architecture and function. So our group consists of four people. The first one is Muhammad Faiz, second is Irfan Nazmi, third one is Ahmad Imran, and the last one is Fateh Nazila. So here is the table content regarding the topic that we're going to talk about in this presentation. So the first one is introduction. What is it? How is it different from CPU and the history? The second one is architecture. GPU in architecture, optimization. Uh, Next one is GPU performance, current development. And the last one is conclusion, the summary of GPU architecture. So as the greetings, welcome to the world of GPU architecture. So imagine a bustling city where thousands of workers are each specialized in a particular task, collaborate seamlessly to accomplish a massive project. That's essentially what's happening inside a graphic processing unit, or which we call as GPU. But instead of construction, these workers are crunching numbers and manipulating data at breakneck speed, making GPUs the workhorses for everything from stunning visuals in video games to complex scientific simulation. So what is exactly is the CPU architecture? So based on the metaphors above, we can conclude that GPU is like a blueprint for the city that integrate the layout for the how these workers, also which we call as cores in this GPU architecture, organize, and then how they access information through memory in the GPU architecture, and how they communicate with each other. Unlike the single powerful core of a CPU, a GPU thrives on parallelism, having hundreds or even thousands of smaller cores that can tackle independent tasks simultaneously. Moving to the next slide. So, what is GPU? So GPU, here we have the diagram of internal computer video expansion card. So first one typically placed on a video card which contains its own memory and display interfaces. Second one is dedicated graphic chip that handles all processing required for rendering 3D project on the screen. And the last one we have the brief history of the GPU architecture. So primitive GPUs were developed in the 1980s, although the first complete GPUs began in the mid 1990s. Okay, so the next one we have the system level view. System level view. Here is the diagram for the system level view. We can see here. And the first point, video card connected to motherboard through PCI Express or AGP, accelerated graphic port. So here we have a circle. In the red line here is the graphic card slot and the AGP or PCI Express, accelerated graphic port. And then the second point, North Bridge chip enable data transfer between the CPU and GPU. Here is the North Bridge and CPU here, GPU here. So they are connected via the North Bridge here. And the last one, graphic memory on the video card contains the pixel RGB data for each frame. So each frame contain a pixel RGB data.
Hi, Assalamualaikum, and my name is Fatina Zila binti Muhammad Nazli, and now here we are at the optimization. There is a unified shader which is about combining different type of shader cores into a single unified shader cores, and then there is dynamic task which is scheduled to balance the load on all core of the GPU. Here are the example of modern GPU hardware. So this is the basic blocks in modern GPU. As you can see, there's a multiple shader core text, and also for the fixed function logic, there's input assembler, primitive assembler, rasterizer, and output blend. And for the fixed function control, there is task distributed. And then there's unified architecture example, which is the AMD Radeon R600 on 2006 and NVIDIA GeForce 8 on 2006 as well. We move on to the next slide. It's about unified shader. Unified shader cores can be considered as multitaskers because they are basically doing the job of pixel shaders, geometry shaders, and vertex shaders that run on the same core. For your information, today GPUs use unified shader cores because it makes GPUs more capable and flexible. Unified shader cores also will prevent a new design of GPUs as it will become more expensive to design a new GPU. To add, these shader cores are programmed using graphic APIs like OpenGL and Directory. In the last decade, there's been an incredible leap in GPU computing power. As you can see, based on the graph, there are more advanced manufacturing processes allowing for more transistors on a chip and architecture improvement like parallel processing. As for GPU memory bandwidth, it's also seen a massive increase. GDDR5 was a standard for a long time, offering bandwidths up to around 28 GB per second. Then came GDDR6, which doubled that to 56 GB per second. And now, HBM, which is high bandwidth memory, is the new kid on the block, pushing bandwidth into the hundreds of GB per second. So both GPU computing power and memory bandwidth have shot up, enabling more complex graphic and computations. Lastly, this is about the current development of GPU and what it would be in the future. Current GPU fixed functions are being abstracted away to ensure the flexibility and efficiency of the GPU. By abstracting away fixed function units, we're making GPUs more adaptable to the future needs and improvements. Newest version of CUDA and OpenGL has included instructions for general purpose computing. In the future, there would be future GPUs that will resemble multi-core CPUs with hyper-threading. That means it will continue to use for machine learning and AI just like today's GPU, and they will be more versatile and efficient. That's all for me. Thank you.
Now we see the difference between the GPU and the CPU. The GPU itself remains the graphic processing unit and the CPU is the central processing unit. It has five different aspects between the GPU and the CPU. The first thing is GPU require less memory consume rather than the CPU that need more memory consume. After that, GPU is faster than a CPU, and then the core contain the GPU is weaker than a CPU that is more powerful than the GPU. But in the instruction method, the GPU consists of parallel instruction processing rather than a CPU using a serial instruction processing. After that, finally, we see the emphasis of the GPU using a low latency rather than a CPU using a high throughput in the computer. After that, we see the history of the GPU. The GPU start recognition in 1996 with a 3D revolution of a 3DFX Voodoo graphic card that implements texturing mapping, buffering, rasterization, but no vertex processing. In 1999, GPU implemented the full graphic pipeline in fixed function hardware that was input in NVIDIA GeForce 256 and ATI Radeon 7500. In 2001, programmable shaders pipeline was added in NVIDIA GeForce 3. After that, it was developed with a unified shader architecture that have been inserted in a ATI Radeon R6 100, NVIDIA GeForce 8, Intel Gamma X3000, and ATI Exynos in Xbox 360 in 2006. And after that, the general purpose of GPUs for non-graphical computer intense applications and NVIDIA CUDA Parallel Programming API was created in 2010, and it was upgraded again into an unpredictable thing that is unprecedented compute power that it was inserted in NVIDIA GeForce GTX Titan Z that have 8.2 T-flops and a Radeon R9 259X2 with a dual GPU card with accurate of 11.5 T-flops in 2014, and it begins uh, even more even more developed until now. After that, we see the GPU architecture. It consists three uh, architectures that have been learned. First is the single instruction multiple data (SIMD). Single instruction multiple data (SIMD) is a single instruction that execute on every vertex or pixel. After that, we see the functional block diagram. Functional block diagram is a high-level representation of the component and their interconnection in a system. Then finally, a shader processor. A shader processor is a computer program that use to do shading, which is the process of computing the color and other attribute of pixel in image or video. It has two types of shader processor, that is vertex shader score or fragment shader score. What is the problem always occur the GPU? We see it has three problems. The first problem is static task distribution. It has unequal task distribute leads to the inefficient hardware usage. That GPUs depends on uniform to work distributes to expose their full potential. And also its load aware task of loading and adoption technique to address the inefficiency of conventional static task scheduling. Then it shows workload distribution. Workload distribution is a frame with many edges. Verticals require more vertex shadings, and a frame with large primitive require more pixel shadings. Finally, it will the dynamic task distributions, that is tasks are dynamically distributed among pixel shaders. That is that it can lead to load imbalance between the processing unit and can increase the overhead of the system, which can also reduce the performance of the computer itself.
Hi everyone. So we are coming to an end of our presentation, but before that, let me introduce myself. My name is Ahmad Imran, and I will present to you the conclusion of our presentation, the GPU architecture. So based on the slides, the GPU plays an increasingly crucial role in computer, especially rendering graphics. As the technology arises, GPU also evolved to execute instructions mainly on graphics. However, there are many computers that do not use high graphics applications. That makes old GPU still relevant until today to run basic graphics needed for those computers. For example, if you ever heard about AMD Radeon graphics, the oldest version of GPU, it is still used until today, but only for the old Windows or old computers with low specs. And also, in addition, GPU still have its importance other than processing graphics, thus making it one of the most important compartment in a computer. So let's dive into the importance of GPU. So first of all, GPU will revolutionize graphics and visual computing. What does that mean? So GPUs power stunning visuals in video games, movies, and 3D applications. So if we have the low specs of computer and the low spec of GPU, it will run maybe not smooth because we have to we have to use low resolution of the video games or even movies because high resolutions require high graphics applications. And also their parallel processing capabilities accelerate tasks like image and video editing. So if you want to use your computer for video editing or graphics rendering, you should use a high GPU architecture. A high GPU. The second importance of GPU GPU will boost performance in diverse applications. So not actually GPU rendering graphics. GPU also go beyond the graphics, enhancing scientific computing, AI, and machine learning. So they excel at parallel calculations, which is ideal for data analysis and algorithm training. So basically, higher GPU used by those people who passionate in their career like data scientists, data analysts, or animations, and so on. So the GPU also specialized architecture accelerates these tasks like simulations, modeling, and data visualizations. And lastly, the importance of GPU is enabling cutting-edge technologies. So GPUs play an vital role in emerging fields like virtual reality, augmented reality, and autonomous vehicles. That being said, those features that we have been used for years, especially the augmented reality and virtual reality, are because of the GPUs. Yes, GPUs executes instructions to make sure we have better experience during our session with the virtual reality or augmented reality. And also, their processing power is crucial for complex calculations and real-time rendering in these applications. Like I said before, to make sure we have the better experience. And I think that's all from me. Thank you for listening, and I hope you enjoy our presentation.